Hello, classmates. Good day to you. I am here to clarify, I hope, a lab that is being executed this week, and I need to clean my whiteboard off, so let me get that done. Okay, we have a lab that was begun on Monday and will carry through Wednesday. And what this is a resistance current voltage lab using the resistance canister from the lab volt trainer. You all have seen this before. We've got 3 banks of resistors. Okay, each bank has a 1200 ohm, 600 ohm, and 300 ohm resistor in there. Now, those are nominal values. What are the exact values? Well, there's no way for you to know that, okay, until you take a fluke meter and measure each one of them. Now, if you look at the front of this canister, you will see that the accuracy of the resistances is plus or minus 5%. Okay, so you've got some good leeway of variation for the actual ohmage, or the value, the resistance value of each resistor. Continuing, the first thing that the lab has you to do is to take a fluke and measure the 9 resistors that are within your canister, okay, so that you can work with the actual values. Now, what you're going to do is you're going to find that there is variation, but it's not going to affect your calculations egregiously, okay, from what I am asking you to do. Now that I'm asking you to build this circuit, and this is probably the main reason for this video, you're going to have a power supply, okay, and you'll see that that's going to be 35 volts when we get ready to apply voltage. Okay, I connect the negative side of the power supply to the first bank of resistors, continue on, and then I have 2 banks of resistors connected in parallel. Okay, my current flows into this bank of resistors, out and back to the positive side of the power supply. Excuse me, I'm thinking for a moment. So what you're going to do is you're going to incorporate the appropriate number of resistors to get 257.143 ohms nominal. Now then, I'll go ahead and tell you, since everybody else I think already knows it, what you will have to do is you will have to turn on all the switches to be able to get 257 ohms. You can get higher values, but you cannot get lower than 257, okay? And you should be beginning to understand why you have to have all the resistors included in the circuit in order to get that value. If you remember, when you put resistors in parallel, the more resistors you add to the parallel circuit, the lower the total resistance, or the lower the equivalent resistance goes. Okay, after the circuit is built, I am asking you to take some measurements, and since we're still new to this game, you'll have to stop and think a little bit, okay, as to what you can and cannot do and how you are to do it. Remember that voltages are measured in parallel, In other words, you place the meter in parallel with a resistor to measure a voltage drop. And if you're measuring current with our fluke, you actually have to insert the meter into the circuit, meaning you have to place the meter in the circuit in series with whatever devices you were trying to evaluate. Okay, I'm back from rescuing myself and my laptop and my recording equipment from the kitty cat. Her name is Tinkerbell. So she was not happy with that. In fact, she's presently sitting on the back of my chair. I just now realized that. So let's see if we can continue with this. Okay. So you've seen the original layout as such. Okay. And I'm going to redraw this. I've got my power supply, which will be 35 volts, and I will send my current in this direction, clockwise is the way I always do it. And I encounter my first group of resistors. Okay. There they are. You recognize the batch of three. That's R1, R2, and R3. And I'll continue down here. And let's see here. How will I do this? So I've got R4. She's not going to leave me alone not until I give her my full attention. R4, R5, R6, R7, R8, R9. Now I'm not showing the switches, okay? They're in the circuit, but I don't have to draw them. I don't have to include them in this schematic. Here she goes. Maybe I can get her to move on. Tinkerbell. Okay, so I've got R4 through R9. So, power supply. It's going to be 35 volts DC. Okay. Current flow. I'll call it I sub T. Now then, you all recognize that the current will flow from the negative side of the battery over to the positive side of the battery. It will come into this first node here. And let me see if I can get a little color in here to help us out a little bit. And it will divide up the part of the current will go through this resistor if I'm using them right, if they're in the circuit. So I've got I sub R1, I sub R2, I sub R3 as it enters this group of parallel branches, okay? When it gets here, again, the current will divide up. Okay, and we'll have current coming down through here, current coming down through here, current through here, etc., right? And they all recombine at this end. Come here and they continue on their way to the positive side of the power supply. Okay, and we recognize that the short plate is the negative polarity and the long plate is the positive polarity. Okay, so there's my circuit redrawn. Now then, what do we need to know? Okay, one of the things I've asked for is I've asked for the voltage drops, okay, across each resistor. And if you recall, for parallel branches, for resistors in parallel branches, okay, the voltage drop will be the same for each resistor. Now, the voltage drop in this circuit will not be 35 volts across each resistor. Right now, it's an unknown to us. So following this group of resistors, I have another group that has 6 resistors. So this 6 comprises a set of parallel branches that will have the same voltage for each, the same voltage drop for each resistor. Okay, 6 of them in this case. But I have to determine what those voltage drops are. So I need to get the equivalent resistance of this batch of resistors, and I need to get the equivalent resistance of this batch of resistors. 3 resistors in here, 6 resistors in here. So let's call this one R equivalent 1, and that's going to be equal to 1 over, well, you know the equation. Right there. I can calculate this equivalent resistance, and I could in fact take these 3 resistors out and replace it with a resistor equal to R equivalent 1, put it in there, and the circuit would behave the same. Here, R equivalent 2 Okay, so that's how I determine what the equivalent resistances are. Now, why would I do that? Because I need to know what the voltage drop across the parallel branch group number 1, and I need to know what the voltage drop across the equivalent resistance of parallel branches number 2. What they would be equal to. Now then, I can replace all of those resistors There's R equivalent 1. Now that's not a very good drawing, is it? I should be ashamed of myself. So let's see if we can dress it up a little bit better. So I have 2 equivalent resistances that I can use for calculations, okay? And that will allow me to calculate or to determine the voltage drop across R equivalent number 1 and a voltage drop across R equivalent number 2. And once I do that, I know the voltage drop across R1, which is the same as the voltage drop across R2, which is the same as the voltage drop across R3. Second equivalent resistance, that had 6 resistors in parallel. Since they're in parallel, the voltage drop across R equivalent 2 will be the voltage drop across R4, voltage drop across R5, R6, R7, R8, and R9. If I know the voltage drop across a resistor, then the current that flows through each resistor is equal to the voltage drop across the resistor divided by the ohms of that resistor. That is Ohm's law. Okay. Now then, these are the equations to get the equivalent resistance of resistors connected in parallel. Okay. This is no longer foreign to us. Still fresh, but not foreign. But if I use the nominal values of the resistors shown on the front of the lamp volt trainer, R equivalent 1, this one, will turn out to be something on the order of 171.428 ohms. R equivalent 2, which has 6 resistors in parallel, will be approximately 85.714 ohms. Now then, I'm asking you in the lab to use the exact values, and what you'll find is they'll be slightly different from these numbers, ever so slightly, but very, very, very close. And in most cases, when we're working with resistances in electrical circuits, nominal values will get the job done. There will be cases where you have to use the exact values, okay, and this is This is not one of those requirements. I want you to see the difference between the exact values and the nominal values and get a feel for what the variation of those numbers look like. So what I have now is I now have 171.428 ohms here and 85.714 ohms here. And that comes up our total series circuit, right? You just add them up to get the total. Will be about 257.143 ohms. Now, why did I do this? Why did I do this? Because I'm going to need to know the current. I need to know the current, okay? And to know the current, I will use Ohm's law to calculate it. I've got my resistance total. I've got my voltage. I can calculate my current. So, Ohm's law says that current, and in this case we're looking for total current, is equal to the voltage applied, because we're looking at the total circuit, divided by the total resistance of the series circuit, using these two equivalent resistances. So I can continue on. That will be 35 volts divided by 257.143 ohms, and that will give me a current. I'll go ahead and cross this wire here with a big arrow. Okay, what do we got? 35 divided by 257.143. So what I can expect is I can expect .136 amperes. Now then, since I have that, I can calculate the voltage drop across this equivalent resistance, and I can calculate the voltage across this equivalent resistance. With that, I know the voltage drop across R1, R2, and R3. And with that, I also know the voltage drop across R4, 5, 6, 7, 8, and 9. Continuing, what I need to know now is I need to know the voltage drop across R equivalent 1, and I need to know the voltage drop across R equivalent 2. Now, why do I need that? If you remember, instead of why do I need it, how do I calculate that? Okay. Now we know that we have a current of 0.136 amps flowing from this plate around the circuit. It passes through R equivalent 1 and it passes through R equivalent 2. Now Ohm's law says that voltage is equal to the current multiplied by the resistance. Now then, let's talk about how we use that. It doesn't have to be the whole voltage, okay? In a series circuit, of course, it will be the total current. But we can also calculate the voltage drops, okay, if we know the resistances, okay? So I do know this resistance, and I do know this resistance. They're not equal, okay, so the voltage drops won't be equal. The only thing that's going to be equal in these two resistances will be 0.136 amps because it's a series circuit. The current has no other path to flow, so it's going to come through REQ1, and it's also going to come through REQ2. It's going to be the same resistance, the same amps, but the voltage drops will be different. So, looking at Ohm's law, I can say that the voltage drop across a resistor is equal to the current flowing through that resistor multiplied by the value of that resistor. Okay? So let's take a look at that a little bit closer here. We'll say that the voltage drop across R equivalent 1 is going to be equal to the current flowing through R equivalent 1 multiplied times the value of R equivalent 1. Okay, does that look right? So, let me get out my trusty calculator here. So, this voltage drop will be equal to 23.3 volts. Now then, we need to know the voltage drop across R equivalent number 2. Now I can calculate it the same way, right? The voltage drop across R equivalent 2 will be equal to 0.13, getting carried away there, excuse me. 0.136 amperes times 85.714, and that will give me this voltage drop. But remember, Kirchhoff's voltage law says that the sum of the voltage drops in a series circuit must add up to be equal to the applied voltage. Okay, so I can do this. Okay, and for giggles, let's go ahead and do it. And this comes out to be 11.6. Well, let's make it 11.7 volts. That's by Ohm's law. Okay, Ohm's law says I've got 23.3 volts dropped across this resistance. I've got 11.7 volts dropped across this resistance. If you add up 23.3 and 11.7, it comes out to be equal to 35. Okay, so that's pretty good. Or I could have done now. Remember, this is Ohm's law. Doodlebug. That's Ohm's law. The other way we could have calculated the voltage drop would have been Kirchhoff's voltage law, which says I could have calculated this voltage using that, which would have been 35 volts is equal to 23.3 volts plus the voltage drop across R equivalent to, right? Let's set that right there for a moment. Let me dress this up just a little bit. Okay, so if I wanted to calculate voltage drop across R equivalent to from Kirchhoff's voltage law, you can see that the voltage drop across R equivalent to would be equal to 35 volts minus 23.3 volts, and that would have given us 11.7 volts. So 11.7 volts here. Okay, so now then, if I go back to my original circuits, which had all the parallel resistors in them, that first group that had 3 resistors will have 23.3 volts applied to each one of those 3. The second bank of resistors, which had 6 resistors in it, will have each 11.7 volts applied to the resistors. And I can use Ohm's law again to calculate the branch currents flowing through those resistors. So what that shows you, what we've done is we've taken the original circuit, we converted it to an equivalent circuit with equivalent resistances, and that made the circuit a very simple series circuit. And I used Ohm's law, okay, to calculate my voltage drops, and also used Kirchhoff's voltage law to calculate the second voltage drop. Okay, now that's not hard. You just have to work 1 or 2 problems and you'll have this down pat. Okay, so now we're back to our original circuit. These 3 resistors comprise, okay, or they make up R equivalent 1. These 6 resistors, these are in parallel with each other. These 6 resistors make up R equivalent number 2. What we did is we determined that the voltage drop across this group right here is 23.3 volts. The voltage drop across this group is 11.7 volts. Okay, great. We did that, right? So big deal. What do we do with that? Now then, each one of these resistors has an exact value. The lab will ask you to determine how much current is flowing through certain resistors. So if I need the current flowing through R1, for example, I can use Ohm's law, which is I is equal to V divided by R. And what that would be, that's going to be 23.3 volts. And I'll use the nominal resistance here. Okay, so the nominal resistance is 1200. So 1200 ohms. Okay, and that will be the current flowing through that single resistor. And I can do this because I now know the voltage drop across this group. And since it is a parallel group, R1 has 23.3 volts dropped across it. R2 also has 23.3 volts dropped across it. You can use Ohm's law to get its current. And R3 has, you guessed it, 23.3 volts dropped across it. So I can use Ohm's law to make these calculations, and I can carry out my lab as a result of that. Okay, so let's just do the arithmetic just for giggles again. Okay, 23.3 volts divided by 1200. So, R1 has 0.019 amperes flowing through it. You can use the same Ohm's law to determine how much current flows through R2, the same Ohm's law to determine how much current flows through R3. Okay, R1 has a nominal value of 1200 ohms. R2 has a nominal value of 600 ohms. R3 has a nominal value of 300 ohms. Okay, so each resistor will have a different current flowing through, a different amount. You do the same thing down here. You can calculate the individual currents. But remember, this group has a different voltage than this group. It's 11.7 volts down here. But Ohm's law always holds true. And it's a very simple law. And all you have to do is make sure that you keep it organized as you work through the lab.